Okay, good. So it's joint work with the people from IBM who hosted me for an internship last year. So let's start off with an example. So many of you have probably seen this application here. It's an Android application called Super Bright LED Flashlight. And when I try to install this on my device, I get this list of permissions that the application requests. If I don't grant all these permissions to the app, then I cannot install the application. Now, probably you cannot see all the permissions that are requested here, but it's probably the first flashlight in the history of mankind that wants to know my location. It wants to know my identity, and it also wants to talk to the internet, so it wants to tell somebody about it. So there's a lot of important work in this field on finding malicious flows between these sources and things in information flow analysis. In this talk, I want to take the more proactive approach of asking the question, what if we allow the users to remove permissions? What happens then? And everybody who has tried to do that can tell you that well, many Android applications will break when you try to do that. And the reason is that they weren't written with this kind of model in mind, so they don't degrade the functionality in this situation. So our problem, our general high-level problem is graceful degradation. So I have a system that uses a resource. I make this resource now inaccessible. And the question is, how can I modify this system such that we avoid system failures in the absence of the resource, and we maximize the remaining functionality? So this is a very general problem, and we study it in the context of Android here. So let's make it a little bit more concrete. I have my Android application that requests a device ID. And I have my resource, which is restricted by a permission. That is the API call to get device ID. And one approach to solve this that has been done in previous work is basically just replacing this by a mock value to basically keep the application running. And this has been done by several folks. So there has been a ShamDroid paper by systems people from University of Cambridge, then a very popular open source tool implementing this. And Google also has played around with this idea recently. However, this doesn't work. So in many situations, a fixed mock value will not keep my application running, and we will see examples of this throughout the presentation. So the goal of our work is, can we use static analysis to infer just the right mock value to keep the application running? And so this is the outline for the rest of my talk. I will talk about avoiding system failures, our first goal, our second goal, maximizing the remaining functionality, and then, of course, our implementation and how this works out in practice. So I'm going to talk about real-world examples. So one of them is the application that you saw before, a piece of code that tries to acquire the device ID in Super Bright LED Flashlight. And another example from White Pages, Caller ID, and Block, which tries to acquire information about my phone number. So these are both like top 500 applications. So this is not some example that is from some random application. So let's look at the first example here. So I have here a piece of code that is fairly standard. It's in this application, but it's actually from Tapjoy advertisement library, so it's used in several applications. Now, this piece of code performs a certain amount of checking whether my resource satisfies my expectations, and then implements functionality or the system fails. So our first goal here is, where in this code can we find the system failures? And for this, we have the following intuition. So in our system, we say that system failures are marked by bad locations in the code. So, for example, that might be exception throwing, error handling, etc. This is essentially the metric that we're using to define whether our system will fail or not. So in this piece of code, we can see, well, we would first now compute a forward slice to basically find out what parts of the code can be influenced by our resource. And then we collect all the bad locations that are in this piece of code. So here we have error logging. So this is a location where we don't want to get to. Here we have a potential system failure if the device ID is null, right? We access it. In this piece of code, you might notice it's infeasible to reach this code, but of course we have to do some analysis to find that out. And there might be some other potential failures somewhere down here in the rest of the code. Now, let's focus on the first system failure here. Our goal is now we want to find out what the resource must look like so that we don't reach this system failure down here. And we can use slight variations of standard tools from the PL community to solve this task. So first of all, to just to basically localize our problem, because of course we have a huge amount of code, we intersect our forward slice that we computed before with a backward slice to give this a slice from source to target that is interesting to us. And then we compute from the we do a backward propagation of constraints from the system failure back to the resource. So this is essentially computing weakest preconditions along this path, plus some filtering along the way, because we know what we're actually interested in. We don't have to collect everything because we only need information about the resource. So in this case, we would find out, okay, it's a small example, so it's relatively easy to see. This is unreachable if the device ID is not null, and the device ID, the length of the device ID is not 0, and it's not equal to these two constants that the application here checks to detect if these are mock values or not. So put simply, so we have a proper formalization in the paper, but this is just to see it a little bit more precise what we're doing, because I want to extend this formula a little bit later. So we just compute this big constraint here. Here's our forward-backward slice from the resource to the bad location. We have the negation of the weakest precondition, and we just quantify this over all bad locations. And then our safe mock is given by the model to this formula. So as I mentioned before, okay, this is all nice and good, but we don't only want to avoid system failures, but we want to maximize the remaining functionality. And for this, I want to talk about the other example that I mentioned before, the white pages call ID and block. Here the application requests my phone number. Of course, this is not necessary to block incoming calls, which is the essential functionality of this code down here. And here we again do certain checks. So the string must not be null, and it must have a length of 10. Here you can see that this is a check that is only true for US applications. So a fixed mocking approach would have to basically know now that this is a US application and I need to fit into this form to find to satisfy the constraints of the application. Now, if I just apply my technique that I explained to you before, there's a simple way out here, right? So if I return null for my resource, I essentially don't execute any functionality, and there are no system failures. So it's a trivial solution to this problem, but it's not a very helpful one, because down here data manager class is initialized, and this is important for the rest of the functionality of the code. So we need a second definition here, and that is functionality in our program is marked by good locations. And these good locations are the usages of the resource. So whenever I use a resource, this implements some part of the functionality, and I want to reach this point. Of course, I cannot reach all of these good locations. I might have alternative implementations, right? So only a part of the functionality can be reached by our mock. So how do I go upon this now? Okay, we have seen here we make use of our resource. So I'm talking about transitive uses, of course, of our resource. We compute the forward slice. We look for the good locations in our forward slice. And we try to reach these points in the program by computing the weakest precondition again, and this time not negating it. So our overall problem now looks like that. So we, as I said before, we cannot find a solution to all good constraints that we infer in that way. So we formulate the problem like this. We want to find a maximal subset of the good locations such that we're still safe, so we avoid all system failures, and we reach this maximal subset of the good locations. Now this ends up to be a max S&T problem, and these are very, very large constraints. So you can have a look in the paper. We have a neat way of dealing with this problem that actually makes this problem tractable in most cases, but I'm not going to talk about this during the presentation. So now, of course, important part in this work is now actually checking out, does this work in practice? And so we have implemented our tool as a program transformation. It's called ShamDroid, and it really so it's really from the APK to the APK, from the original APK to an APK that does not use the particular resource anymore. So we use the w.r.t static analysis toolkit for our analysis here. And we make use of a bunch of other projects that helped us implementing our vision here. So first of all, we need to scan for the API calls that actually use permissions. For this, we made use of the pscout project that found a mapping between API calls and permissions. Then we use w.r.t to build call graphs and perform the slicing of the code. We do the constraint analysis, and we pass the resulting constraints that I've shown you before to Z3 or an extension of these three, actually, these three STR, which was published at FSE 13, that gives us the ability to express string constraints, which is very important for this application, of course. And then finally, we get a model to this constraint. And we instrument the original program, so we replace the resources. Here we have a library of mock definitions, which basically map variables in the model of our constraint back to code that creates the mocks that I use later in the program. And then finally, we merge back some non-executable data in our restricted APK, and we can run it as before. So as for the experiments, so we evaluated this in two ways. First of all, we just ran it on a lot of applications and just asking ourselves, well, can we actually satisfy the inferred constraints? And how efficient is our analysis in these cases? And second of all, the qualitative experiments, where we took a subset of these applications and actually ran them on the device without the permission to observe whether we actually achieved graceful degradation. So we targeted here only the location and phone identity permissions. So our experiments are restricted to these two permissions. So the large experiment here is on the top 500 free applications from the Google Play Store, at least at the time back when we wrote the paper. 310 of those had used these targeted permissions, so either location or phone identity. And we ran our tool in 32 parallel instances, and then after 46 minutes, we had analyzed all of these applications. Now, let's look at some of the results. So here are the statistics about the bad constraints. So in 96% of the cases, we were able to actually satisfy the bad constraints. So we were able to avoid the system failures in this case. And only in the 3% here, we were not able to satisfy them. There's two things to say about this. Well, first of all, a nice feature of our tool here is that we know when we fail. So we can actually go back and tell the user, okay, here for this particular permission in this application, I'm not able to satisfy the constraints that I inferred. Second of all, if we fail, we're still as good as the previous work. So we can still plug in a fixed value and try our best or hope for the best. And then the situation about the good constraints, so the functionality that we're trying to reach. Here we satisfy 90% of the constraints, and the 9% we do not satisfy them. Of course, as I mentioned before, we cannot satisfy all of them because you may have alternative implementations, and then so 100% is not actually not achievable here in this case. And then finally, we took so 27 applications in here that we systematically selected from these 500 applications. We describe it in the paper how we selected it. It's not just like the applications that we liked, but it's basically applications that imposed interesting constraints about the resource that were interesting to us in this case. So as a baseline here, we basically just ran all of these 27 applications, and in the baseline, we just removed the permission, just to prove our initial expectation that many of the applications will not gracefully degrade in the basic scenario. So here you can see that in 17 cases, the application crashed when we tried to access the resource. So this was expected from the beginning. And then we compare about XPrivacy, so the open source tool that I mentioned to you before, that is very popular and has many users. And here you can see an interesting result, actually. So we have 5 cases where the application crashes with a fixed mock value. We have 4 cases, sorry, that just hang. They're in some state in the code where they cannot proceed anymore. And we have 3 cases where actually, and that was very surprising to us, where actually the tool leaked the private information because it's a framework-based approach as opposed to our rewriting-based approach. So they didn't really revoke the permission and let some of the calls to this private resource through. And then our tool actually performs very well on these applications. So here the gray bar, of course, we don't mean that the application works just as before, but it works modulo the functionality that really requires this particular permission. So in this case, in 26 of the cases, we were able to still use the application modulo, for example, seeing our location in the map and so on. Then finally, just a quick look at some examples. So here, for example, you have the kayak tool, which you can use to buy flights online. This one in XPrivacy, when I press airports, it will crash because it tries to find the airports in close proximity. In our case, it will basically just say, well, I cannot search for close airports in this case, right? So we avoid the system failure here. And in the WhatsApp case, WhatsApp with XPrivacy gets stuck because it tries to verify our application using text messages. Our tool avoids this by basically maximizing the functionality and resorting to the code that does not text message verification but voice verification and skips this part of the implementation. And then concluding my talk, so graceful degradation is, I think, an interesting and relevant PL problem that hasn't been targeted so much before. It requires reasoning not only about failures but also about the functionality that we can reach, and especially this part about maximizing the functionality seems to be a key concept here. And finally, it can be effective in practice. And that concludes my talk, and I'm happy to take questions.